Hello, hello. All right. So today, I just wanted to go over a little bit of what Dirac notation for quantum mechanics. I know a lot of people are probably struggling with this, and I want to see if I can help out somehow. So in quantum mechanics, a lot of times we do a lot of fancy integrals with notation like this. And so, hold up, let me just double check this real quick. And so one thing, uh, these represent wave functions, which represents like you could think of a probability of where a particle lies, and we do this to calculate some properties of these systems, right? And so this is actually the longhand note form of this, which is written in Dirac notation. Okay, and so this symbol right here, these two symbols, this is known as a bra, and this is known as a ket. And so when you put them together, it represents an integral of some form. And so whenever, if you see this alone, this just represents a wave function, this alone. So it could just be, sometimes it'll be shown like this, and it could represent some type of constant times a function, say like sine of x, right? And, but remember, if you have it this way, what this represents is a complex conjugate of the system. And so if we assume that C might be a complex number, you just do the complex of it. Sine of x is just, it's real valued, so it just remains the same. But if you put these two things together, this represents an integral of all space of these two. And so this would be drawn like this. It might be negative infinity to infinity, or say 0 to a if you're like in an infinite square well. And you'd have C sine of x times C sine of x dx. And so you would just integrate this and you'll get some type of value. And so um, uh, this isn't the end of it. So one thing that you might end up seeing is some type of form where they'll put something in between here, say V, for example, like potential. And so the way this is written out, it's the same thing, but you actually stick this V, what's known as an operator, in the middle. So you'd still get your C constants. I'll just move them to the side. Or in this case, I'll just try it out like this first. V this. And so when you actually draw it out in this form, it would be the integral C star sine x, and then V's in the middle. And the order might actually matter here. So you want to actually put it in the correct order as needed. Dx. And so I didn't tell you what V represents. V could just be a constant, but it could also represent an operator, say like the derivative of the function. And so if you were to plug in the derivative here, this would end up looking something like this. And V is just the derivative. We'll move, and to see this derivative, the way math works is the derivative sign applies to this part. Dx. And then so you would solve if this like this. The constant you can move out. So you'd have C star times C sine. And then what's the derivative of sine? It's cosine. Dx. Right? And so this is just Dirac notation. It actually makes systems a lot easier to work out. And so another thing that you'd actually be able to note is that this is assuming that the system's one-dimensional. You have to recognize what dimension are we dealing with. So our integral setup for this can actually be three-dimensional, right? So it could have three dimensions, and this would be negative infinity to infinity for all of these integrands. be dx, dy, dz. But a lot of times, if we're dealing with something with spherical symmetry, you're going to want to use spherical coordinates. So say if you're integrating something with like a hydrogen atom or something that's is better to integrate sphere-wise. So all of space in here might look a little different. You still have these two these two psi functions, but then you got to include the Jacobian of this integral form. You have dr, d theta, d phi. And for the dr, this goes from 0 to infinity. For this theta, 0 to pi. And for this phi, 0 to 2 pi. And so these two integrals are actually the same. It's just a different coordinate system. All right. And so another thing of these systems that might be important, or it's the first kind of problem you'll usually get, is when they tell you normalize the system. What it means to normalize the system is when you get this integral, the answer has to equal 1, right? And they might give you an initial wave function saying this is equal to some type of constant times a times another function. And when they tell you normalize it, what they're really saying is what value does a have to be such that this is true, such that when you integrate this, you get 1 out. So if we were to set this up, this is actually an integral. And remember, this is all space integral. So, and this is in spherical coordinates. So we'd actually want to use this coordinate system, right? And so I'll just leave out all this and you can fill it out yourself. So you'd have a times er this. Remember, it'd be the complex conjugate times a er this. Oop. And so you'd end up doing r squared sine theta dr d phi, or d theta d phi. Okay, and so you'd work out this integral with these specific numbers here, and you'd end up getting some answer out. You'd have a star a, which you could just assume it's real valued, which is, so this would just end up being a squared times the value of the rest of the integral. And so the rest of the integral value we'll just call it I right now. And remember, you have to set it equal to 1. And so you basically take a squared is equal to 1 over this integral value I, and you take the square root of it. And you'll get a is equal to the square root of 1 over I. And that's how you basically solve like a normalization type problem. And so the same process occurs when you want to apply an operator. You basically take this and you just do the same thing. You just do your regular integral of all space, but now you just apply this operator in between. Oop, there shouldn't be a complex conjugate here. And sometimes you might see this notation, dv. This is shorthand for all of the volume of the whole entire space. And so that's what this thing represents. And so this is just kind of shorthand notation for quantum mechanical systems. This is just for mostly for continuous or just other functions. Later on, you might actually run into occasions where like the wave function might represent a vector, and this might represent a matrix. And then you just basically just doing some linear algebra type problems where you have a vector and then you have your matrix and you multiply it by another vector. And so this will actually get you a scalar out. A scalar is just a regular number. And so all of these should give you scalars out. So keep that in mind. These are functions. These represent functions. When you put it together, it's an integral of a function. And the whole entire integral should end up giving you a scalar out. So I just wanted to make this just to help some people out if they had any questions on that. So hope that helps.